charge for deciding weighted parameter. It's an empirical equation. It is giving me a value that my stable weighted parameter can be 1890 feet for this value of discharge. For very wide rivers in plain areas, I can say that my wetted parameter is approximately equal to width of flow. Reason being the width of flow is significantly or very much larger as compared to depth of flow. The wetted parameter is approximated here as width of flow. Further, we discussed that this estimated width of flow has to be multiplied by a factor known as Lacey's looseness coefficient. The purpose of applying Lacey's looseness coefficient is if as I have used maximum value of discharge as for determining the wetted parameter, it's not necessary that maximum discharge is always occurring. In most of the time, the discharge passing through the barrage will be lesser than this designed discharge. And lesser discharges, there are chances of formation of shoals or sometime islands. I was before your class, I was seeing this aerial view of Khanki Barrage. If Ms. Cursor right now is moving along Khanki Barrage, if you observe the upstream side of Khanki Barrage, there are several islands formed. The guide in between the guide banks, in between the two abutments, there are several islands are formed. It happens that after construction of barrage, we have we have provided a width which is according to Lacey's equation, but the design discharge is lesser than this. The actual discharges or most of the time lesser than the design discharges in most time of the year. So sediments will start settling, and as time goes on, they will form small islands. So they will be reducing the width of flow or available width of flow. If available width of flow is reduced and whenever the design discharge occurs, velocities will be increased. They will be smaller channels. If you see, it's a separate channel, another channel, upstream of the barrage, just upstream of the barrage, one, two, three, four different channels are created just upstream of the channel. And so for the design discharge, velocity will be increased whenever it's occurring. So to safeguard against this, we apply a factor known as Lacey looseness quotient and multiply the calculated bit by 1.8, 1.1 to 1.8. Generally, 1.8 is for plain areas, or greater value is for plain areas as there are more chances of sedimentation or shoals formation in plain areas, and lower values are for hilly areas where there are lesser chances of sedimentation. So this decides our total width or width between the abutments or clear width available for flow. This 3400 is this starting from right to left bank of the river at the barrage location. Of that 3400 feet, we need to provide certain bays. For regarding bays, we were few students were facing difficulty in the last class. So let's see what let's see this Kotri barrage information on it. You see, students, it's another photo of Kotri barrage. Uh, we cannot right now see the Weir constructed. It's the upstream side of Poultry Barrage. On the upstream side, a pool has been created. So this water will pass through the weirs or below the gates, passing in between these spaces. Space between each two different piers is termed as a bay. It's one, two, three, four, five, six, seventh, eighth, ninth, tenth different bay. Here is a divide wall. It's a thicker wall. See here. Kotri Barrage, it's on Indus River, location in Sindh province. The barrage was completed in 1955. It's used to control water flow in the Indus for irrigation and flood control purposes. It has a discharge capacity of 875 cusics. Uh, in our case, it's 500,000 cusics. It's here for Kotri Barrage, it's 875,000 cusics. It's gate controlled Weir type barrage with a navigational lock. There is a navigational channel. I showed you in the last class. In the last class, I'll show that you again. The barrage has 44 bays. These open spaces, the number of open spaces are 44. Each is 60 feet wide. Each bay is 60 feet wide. The maximum level of the water level on the upstream side is 13 meters. It feeds certain canals. So we'll be designing more or less a barrage like this, or it's not only Kotri barrage, rest all of the barrages in Pakistan or other or also the locations are more or less the same. So last class we proportioned barrage. Our total length was coming out to be here. It was around 3,400 feet. We have to proportion that 3,400 feet has to accommodate bays, tiers, fish ladders, and divide walls. So just try few values. 50 bays at 60 feet. For 50 bays, we'll be requiring 49 piers. Of the 49 piers, there will be two divide walls and a fish ladder that can be provided along the divide wall. Some generally used dimensions are assumed in the book or tried in the book, you can use the same values. And summing all these 3,000, 329, 26, 30 feet, width between the abutment is 3,385, and width for water to flow over the barrage is 3,000 feet. This width 3,385 is upstream, just upstream of the weir, and this 3,000 is the clear width available for flow. So the specific discharge upstream of the weir will be discharge over width available for flow on the upstream side. And discharge over the crest will be discharge over width available or width of the weir, width available for flow to occur. I have calculated these two discharges. These two values will be further used in almost every step. In almost every step further, I'll be using the value of discharges, and I'll be using these two values, and further in a step I'll be discussing today, we'll be calculating these discharges for three different states: a normal state, a retrogress state, and a accreted state. इसको भी हम आगे मैं दोबारा what was at retrogression equation discuss होगा. Is any questions up till this step?
सर आपने कहा था पेयर्स 49 होंगे लेकिन ये 47 लिखे हुए हैं.
47 means total number of divisions of 50 bays is 49. If there are 49 divisions, or we can provide 47 piers and two divide walls. 49 sports, I can say. 49 required. Of those 49 piers, two will be replaced by a thicker wall.
Okay,
is it clear? ये एक और क्लास में भी क्वेश्चन आया था. प्लीज इज इट क्लियर?
yes
Rest
it is
of you.
clear.
The next step, an empirical equation, no equation of Lacey's slope. In this equation, S is the channel bed slope, F is a factor known as Lacey's silt factor, Q is Discharge. In my next step, I'll be requiring a value of Lacey's silt factor. I'll be applying certain empirical expressions for design, and mostly I'll be following Lacey's silt theory. The detail of Lacey's silt theory will be covered in theory class. Very briefly, I am informing that Lacey's theory is giving several expressions for a stable channel. And by stable channel, I mean a channel which does not covers and which does not silts. If there is covering or erosion, it is instability. If there is sedimentation, it is kind of treated as a kind of instability for uh, earthen channels. It gives several expressions and we use those for barrage design. And mostly in Indian subcontinent, the Lacey silt theory is used. The Lacey silt theory was developed, or these expressions were developed by working on several good working channels or several satisfactory working channels in Indian subcontinent. So that will be again discussed in theory part. Right now, I'm using another expression, Lacey's equation, from which I calculate Lacey's field factor. Channel bed slope is given. If we again see this given data, this given data uh, is prepared after carrying out survey at a barrage site, after carrying out survey at a feasible barrage site, discharge measurements and channel bed slope measurement done at site. These values can be very easily measured at a particular as a feasible barrage site. The channel bed slope is given data. From this given data of channel bed slope is given, discharge is given. I have calculated a value of Lacey's silt factor here. Third step is fixation of crest level. We are given a riverbed level at 582 feet. If I show you again the sketch, the riverbed level is 582 feet. The upstream complete flow level is generally kept at the riverbed level. It is 589, the crest level that has to be estimated and designed after applying knowledge of hydraulic engineering, the thing which we have already studied in hydraulic engineering. तो उसके लिए I'll start with assuming a value of efflux and weir height. Efflux is raise in water level after construction of a weir. Efflux is raise of water level after construction of a weir. So initially, the solid line is the riverbed level and dashed line is the highest flood level. After construction of a weir, the water level will raise. This raise in water level is termed as efflux. The highest value just upstream of the weir is termed as efflux. And we have to start by assuming a reasonable value of efflux. For us, right now, we are doing first design of barrage. We haven't discussed or you haven't seen any design of barrage up to now. So assuming this value as 3 feet for your design case, select this value in between 2.5 to 3.5 feet. After carrying out other design calculations and seeing what is actually happening at site, you can as easily estimate this efflux value. This assumption is based upon technical experience. Another weir height is assumed as 6 feet. These both are assumed just by judgment, engineering judgment and experience. Scour depth is the depth of flow after scouring has occurred. So please, इसके लिए please, you have to remember this thing that the scour depth is depth of flow. If I mark scour depth on this sketch, if I, This covering has occurred or erosion has occurred. It has created a pit like this. Cover depth is depth of flow. Please remember this. Sometimes by mistake we do that if we consider cover depth from riverbed level. ठीक है इसमें गलती I am repeating कि chance of error is some student might think that this cover depth is depth of this covered pit. It's not like that. It is the depth of flow or difference between the water level and the maximum expected covering or the riverbed level will come at this location. Cover depth, first cover depth also Lacey's theory is giving us an expression for calculating cover depth that is zero point 0.9 cube root of discharge over Lacey's silt factor. Here, which discharge should be used? In last step, we have calculated two values of discharges. The discharge just upstream of the weir, a discharge just upstream of the weir, and a discharge passing over the weir. Any guesses कि which discharge should be used here for calculating scour depth?
Upstream वाला.
Exactly, upstream wala. Upstream is the discharge between the abutments. That is also mentioned here. The cover depth is 19.96 feet. At 19.96 feet means the riverbed level will is expected to go 19.96 feet below the highest flood level. Head of water above the weir. In this case, I can say that head of water is depth minus height of my weir. Cover depth is the depth after the covering has occurred. We are considering an adverse case scenario. The head of water above here is calculated here as depth of flow. Depth of flow considered as the cover depth, and P is the assumed height of weir. 13.96 is depth of water above the weir. Velocity of approach will be discharge over depth. Discharge, upstream discharge or discharge between the abutments, and depth is cover depth. Velocity of approach. Velocity head is v square over 2g. Energy or specific energy over the crest is depth plus velocity head. In our book, the depth has been denoted as or static head has been denoted by a capital H, and small h is denoting velocity head. Static head capital H, velocity head as small h. So capital H head of water plus velocity head. Total the specific energy over the weir crest is 14.81. By our assumptions, we have calculated a value of specific energy which will be available over our weir crest. E1 is denoting specific energy upstream of the weir. In last step, I have calculated energy over specific energy over the crest. Next, I am calculating energy over the energy upstream of the weir crest. So on the upstream side, I have in previous step calculated velocity of approach. 0.85 is the velocity of approach. D naught is denoting depth of flow. Depth of flow is given. We are given a riverbed level at 582 feet. Highest flood level without barrage is 600 feet. This is the depth of flow before construction of barrage. 582 minus 600, or the difference of 600 minus 582, that is 18 feet. Specific energy is depth plus a flux. It's the total depth, 18 plus 3, or I should have written it. तो मैं इस तरह भी लिख सकता हूँ 18 plus first 3 then 0.85. 18 is depth of flow without barrage. After construction of barrage, we are assuming water level will raise by 3 feet and plus 0.85 is velocity head. Specific energy upstream of the weir. So upstream USEL is denoting upstream energy level. Upstream total energy level will be specific energy plus the reduced level of riverbed. The riverbed level is given 582 feet. Upstream energy is 21.85. So upstream energy level is coming out to be 603.85 feet for this provided for this assumed efflux and weir height. The crust level should be the difference between upstream energy should be lower by upstream energy level by E naught. E naught is specific energy over the V crest. Upstream energy level minus E naught. Upstream energy level calculated in previous step. E naught calculated in last slide. इन दोनों की difference से our reduced level of V crest is decided, or we can set this as our the crest level. In your books, this is explained on this sketch. Total upstream energy level has been calculated. The difference between upstream energy level and this specific energy over the weir crest that decides our crest level of the weir. After setting this crest level, we need to check either our design discharge can pass over the sphere or not. We have to apply the expression for calculating discharge over a weir. For discharge over the weir, the expression was already studied in fluid mechanics 2 by 3, 2g, c, l, h. अच्छा ये there is a mistake, that is h raised to the power 3 over 2. 203 into 2g and c, they are a constant term for a weir. So the expression for discharge over weir in, is generally is simplified as QLH raised to the power 3 over 2. Sorry, it should have been QLH raised to power 3 over 2. I'll use this expression for calculation of discharge, where I am having a certain length of weir, which is 3000 feet. Head of water, we have calculated right now above the weir. C is unknown. For calculating or for seeing a value of C, I'll be using a graph that has been developed after experimental studies. This graph tells us a value of coefficient of discharge corresponding to various H over E naught, where here the small h is denoting weir submergence. Small h is the difference between the downstream water level and crest level. If the crest level is lower, the weir is submerged. If the crest level is above the downstream water level, it's not a submerged weir. And E naught is the specific energy over the weir crest. We have calculated a value of specific energy over the weir crest, and will be calculating a value of weir submergence. From the ratio of H over E naught, I can use this curve for determining, say, for example, my H over E naught comes out to be 0.85, corresponding to a value of 0.85. I'll obtain a value of C dash over C, where C is equal to 3.8. C dash is the actual coefficient of discharge. So the coefficient of discharge is calculated in the next step. The maximum downstream water level is 600 feet. This can be seen from a rating curve. For our case, 600 feet is the highest flood level without barrage. Without barrage, the downstream conditions they won't be changing. On the downstream side, water will come back to its original water level, original depth of flow. So on the downstream side, there are no changes. On the downstream flood level is downstream water level is the highest flood level as in the given data. 600 feet, or it can be seen from this rating curve also. This rating curve and another curve for seeing the function of discharges, they are also given in the solved example. This is figure 3.1 in the appendix. Appendix part of chapter 3 is a solved example of a barrage design. From our discharge is 500,000 cusics. For 500,000 cusics, there, if you see here, there are three lines: a normal state, an accreted state, and a retrogress state. I'll be discussing these retrogress, normal, and accreted state later again also in our class today. For now, for normal state, the given value is the same. For design discharge of 500,000 cusics, the water level or the highest flood level is 600 feet. 600 feet here. And I said that for seeing that Gibson curve, I need a value of Weir submergence, that is difference between downstream water level and crest level. Downstream water level is 600, crest level is 589.04. The difference is 10.96. The value of Weir submergence denoted by a small h. E naught is the specific energy over the Weir crest calculated in previous slide. At the in this step 3, 14.81. So here there is a ratio of 10 over 14, that is coming out to be 0.74. For 0.74, it's around the C dash over C value is around 0.84. C dash over C 0.84 from this Gibson's curve. The actual coefficient of discharge can be C dash over C is 0.84. So C dash will be 0.84 into 3.8. C dash is 0.84 into 3.8. So C dash or coefficient of discharge to be used is 3.19. The discharge is CLH is power 3 over 2. Here it's slightly changed to C. L is the width. H has been replaced here by energy head or specific energy. C is 3.19. Width, clear width means the clear width available for flow is the width between the abutments. No, sorry, width between the piers calculated in the first step. We are having 50 bays at 60 feet. We are having 3,000 feet available for flow to occur. Rest of these are obstructing the flow. 3,000 into 14.81, 14.81 specific energy is 14.81. Our calculated value of the charge is coming out to be 545,437 Q6. It is greater than our design discharge. If this value is coming out to be lesser than your design discharge, uh, revise the assumed value of weir height and efflux. We started this step by assuming a value of efflux and weir height. If the discharge value is less than our design discharge, repeat the value of assumed efflux and weir height. If that is greater than our design discharge, it's okay. But sometimes it may happen my design discharge is 500,000 Q6. If this value comes out to be say 700,000 Q6, we are going way ahead of our maximum expected discharge. For further steps, be within plus 10%. Don't go beyond that. Be within plus 10 to 15%. Don't go beyond that. But simply if that is greater than our design Q value calculated is coming out to be greater than our design discharge, it's okay. If less, obviously this weir cannot pass that design discharge. Next step is design of undersluices. We have discussed in parts of a barrage the base at the extreme end of a barrage are termed as undersluices. We'll again see this in review of the barrage. The base at the extreme end, they are separated by divide walls. Undersluices are always on the side where they if there is on a canal. If the canal is only on one side, say if the canal was only on left side, there would have been only one undersluice portion. If the canal is on both the sides, we are having two undersluices. Let's see photos of some other barrages also. If you see this Khanki barrage, on this Khanki barrage, and there is only one undersluice on the left side. It is an image of Rasool Barrage. Also for Rasool Barrage, they canals only on left side, undersluice only on left side. For this canal also, this is Kadrabad Barrage. You see this Kadrabad Barrage. These curved walls are we have discussed them in our. We see again the
Guide
part
banks
of
there were.
yeah, guide banks. These are guide banks as discussed in our last class. These are guide banks of this barrage. Undersluice only on one side, left side, that is separated by a divide wall. Rest are normal bays, and these 4 or 5 bays are, let's see how many bays it is having as undersluice. For this barrage, there are 5 undersluice bays, 60 feet. For this barrage, there are also bays at 60 feet, 5 undersluice bays. So for our solved example also, I can for any design, we can start by assuming some number of bays as undersluice. First is starting with fixing the crest level. The crest level of undersluices is kept lower than the main weir. If this is showing the main weir, if there are two undersluice portion, the undersluices will be lower than the main weir. The purpose is to divert water towards these undersluice portion in case of low flow season. Whenever we are having lower flows, if the weir was of same height, the water would have been dispersed. If a channel is provided which is having lower bed level or this weir, the wall height or weir height is lower, the flow will be diverted towards these lower heights. So for this purpose, the undersluice portion is generally kept lower than the main crest level. And the design, this step is started by assuming some value lower than the main weir. In last step, we have decided the crest level of main weir as 589. Crest level of undersluice is 589 minus 3, 586 feet. Assume some number of bays. Right now here it's just assumption. So total width of the undersluice will be each bay is 60 feet wide, 5 bays, and we are having 2 undersluices. One on the left side, another on right side. The total width of undersluice is 600 feet. So the discharge through undersluice is Specific discharge to undersluice. Here we assume there is some concentration. If 166.7 is the discharge path, specific discharge over the weir. Specific discharge over the weir is 166.7, and we have provided a lower weir height here. We are assuming some concentration to happen, and we are assuming that concentration to be 20 times more than the main weir. 1.2 times the discharge over the weir, 1.2 times 166.7, that is around 200 cusics per feet. Again, calculate the scour depth as in previous step. Scour depth for undersluice position. Velocity of approach for undersluice position. For this velocity, use this value of discharge passing through undersluice. Velocity is Q over Y. Y, again, we are assuming depth as our scour depth as our depth of flow. Velocity head is V square over 2G. Upstream energy level, again as done in the previous step, riverbed level plus specific energy. On the upstream side, riverbed level, on the upstream side, that was noted by E1, which is equal to depth, velocity head plus efflux. Riverbed level plus depth plus velocity head plus efflux. In the undersluice portion, the upstream energy level is approximately 604 feet. E naught is specific energy over the VA crest. So that can be upstream energy level minus crest level of undersluice. Here we have already decided the crest level of undersluice. Crest level of undersluice is 586, 3 feet below the main weir. So specific energy here is 18 feet. Weir submergence, upstream energy level minus the flux minus crest level. If we do this also, I can obtain a value of Weir submergence. Upstream energy level minus the flux करेंगे, that will be near to downstream water level minus the crest level, that is Weir submergence. HOE naught 0.83. For 0.83, consult this Gibson curves and get a value of C dash over C. This C dash has to be found out, and C is 3.8. 4.83, C dash over C is 0.76, and C dash will become 3.8 into 0.76, 2.89. Discharge through undersluice, say denote that by Q1 and Q3. And discharge through main weir is denoted by Q. Discharge through undersluice is C dash for undersluice portion, W for width of undersluices only, E naught specific energy over weir crest and undersluice portion. So discharge passing through undersluices is 132 cusics. Discharge through main weir is C dash. Please remember here the C dash as determined in the last step. 2.89 is for undersluice. 3.19 was done in this last step. 3.19, where we also in the last step we were seeing Gibson curve and determined a value of coefficient of discharge 3.19. This 3.19, if our total width of weir is 3000, of that 3600 is undersluice, 2400 left is the main weir portion, E naught specific energy over the weir and main weir portion, except the undersluice portion. The discharge through main weir is 436, discharge through undersluice, whenever the maximum design discharge will occur, 132 cusics. Total discharge which this weir plus undersluices can pass is 569 cusics. That again should be greater than our design discharge. That should not be less than our design discharge. For my case, that is 500,000 cusics. For your case, it will be slightly different. You have to compare this value with your design discharge. Plus, you have to see, do not go beyond 10 to 15%. Please remain within that range of 10 to 15%. The design discharge should be greater than this desired discharge should be greater than should be within 10 to 15% greater than the design discharge. It should not be lower. If we go beyond that, we are providing providing extra safety. So related to this part of our discussion, you have to read the theory related to barrage from your referred textbook. जो हमने चीजें last time I must have you let me show you again कि all of these things which I have discussed are from this book. Chapter 3 of this book. I have shared this book with your Sia just before the class. Please go through this article 3.1, 3.2, 3.3, 3.4, and 3 point up to 3.5. Or also, but no, we can go. You can also go through 3.6, 3.6, 3.6, 3.6. We have discussed what is retrogression and retreation. I'll discuss that again also today. Let's go read up to this article 3.6. Take sketches of barrage profile and plan as made in book. Setting of crest level and main weir for undersluice portion. For your case, for your class, I will give you a value of design discharge. Rest of the data will be same. After the class ends, I will share this with your CR. This value of maximum design discharge. These slides all are also. We were discussing that they can be three different states of river. As said, I will explain them later also. A normal state, a retrogress state, and accreted state. Normal, retrogress, and accreted state. Retrogression and accretion, they were discussed in the last class, as I will be repeating the same thing. Okay, we see this. We see the sketch of barrage. Construction of a barrage has raised the water level. Raising the water level for a value of discharge will reduce its velocities. Reduced velocities will cause sedimentation or silt particles to settle on the upstream side, and water carrying less quantity of silt when after passing over the weir, the water passing over the weir is carrying lesser quantities of silts. And after passing through over the weir, the water for this flow, which was carrying certain quantity of silt, is now carrying lesser quantities, so it will pick silt from the downstream side. It may cause a scoured pit on the downstream side. This is termed as retrogression. This phenomena is termed as retrogression, and it's a reversible cycle. As after time passes, as these height of these sediment layers increases, this will again increase the velocity. Increase in velocity will cause erosion of uh, this sediment settle here, and these settled sediments will be again these eroded sediments will again be settled on the downstream side, bringing the river back to its original position. This is termed as retrogression, and this opposite phenomena is termed as accreted. We have to see our barrage for all these three states. What will be there? What will be the situation in the normal? What can happen in the accreted state and what can happen in retrogress state? For this, The fifth step is determination of water and energy levels. Here it's GY. Right now we have water level for only one state, normal state. Water level is the existing water level plus the assumed value of a flux. It is our water level right now, and that is done only for, if you see this table, we'll be carrying out further calculations tabular form for normal state and a discharge of 500,000 cusics. For a value of design discharge, we are having a value of water level, but we do not have water levels for lower discharges. We are having a water level for 500,000 cusics, but we do not have any value of 250,000, 125,000, or any other lower discharges. Also, we do not have right now, or we haven't estimated what can happen if the discharge greater than design discharge occurs. The first column is telling us this value has to be inputted. This input is 500. First value is 20 times, 20% greater than design discharge, or 1.2 times design discharge. Second value is 1 time design discharge. Third is 50%. Fourth is 25%. That is explained at the bottom also. The column 1 is 1.2, 1.5, and 0.25 times the design discharge. The same for retrogressed and accreted state. For retrogressed state, 600,000, 500,000, 250,000, or here the solved example is doing this only for 250,000. You can do this for lower value of discharges as well. We'll see for different values of discharges what will be the water levels. The purpose of knowing water levels, one of the purposes is we have to decide the height of guide bank as well. What is the maximum needed height of guide bank? That will be determined by these expected water levels. Regarding these discharges, downstream water levels or water levels in normal state are given in form of this rating curve. For a discharge of 500,000 cusics, the downstream water level is 600. For 1.2 times or zero point 0.6, for 1.2 times a desired discharge 600,000 cusics, the downstream water level is around 602 or 602. It's around 600, in between 600 and 605, around 602. Similarly, for 250,000 and 125,000. 250,000 value can be seen from here for a discharge of 250,000 in normal state. Water level can be seen from here. Similarly, for 125 also can be seen from this rating curve. Fill the second column of this table with the help of the hydrograph or rating curve given. It should not be hydrograph, it's a rating curve. On this next slide, I'm showing this table filled for our values. The downstream water levels are seen from this rating curve. Third column is assume a value of a flux. It's an assumed value as was done in step 4, where we were setting the crest level. We assumed a value of a flux. Start with the first value. Assumed value of a flux is 2.5. If the assumed value is 2.5, the upstream water level will become downstream water level, which is the water level in absence of barrage also, plus a flux is upstream water level. Upstream depth will become upstream water level minus riverbed level. These are explained at the bottom as well. Column 5 is upstream water level minus the riverbed level. Column 6, specific discharge over the weir. Discharge as in column 1. divided by the width of weir, that is 3000 for the total weir. Explained at bottom also, column 6 is q over weir, q over width of the weir. Column 7 is velocity, velocity is q over y. For here use y as the original depth of flow when normal. Q is discharge, y is depth of flow, y is calculated in column 5. H naught velocity of approach, v column 7 square over 2g, column 8 is v square over 2g, column 9 is velocity head, sorry, the column 9 is depth of water over the weir. That depth of water will be upstream water level minus the crest level, that is depth of water passing over the weir. So specific energy becomes velocity head plus depth of water over the weir, head of water above the weir, specific energy over the weir. H is weir submergence, that is difference of downstream water level and crest level. Column 11 is downstream water level minus the crest level. H over E naught, H over E naught, column 11 over column 10. H over E naught is determined to consult this curve for getting a value of C dash over C. For this H over E naught, see a value of C dash over C that is written here. C dash is zero point 0.8, this column 13 into 3.8. Column 15 is just simply E naught raised to the power 3 over 2. 3 over 2. 16.24 raised to the power 3 over 2. And last column 16 discharge over the weir is that is mentioned at the bottom also. C dash into E naught raised to the power 3 over 2. The total discharge is C dash into E naught raised to the power 3 over 2 into width of the weir. Specific discharge will be C dash into E naught raised to the power 3 over 2 without the width of the weir. Column 15 into width of the column 15 into column 40. That is specific discharge over the weir. And total discharge is multiply specific discharge by width of the weir. For my case, that is 3000. In this table, if you see, there was one assumed value. You have to change this assumed value until our column 1 is equal to column 17. If, say, for example, I assume the value of a flux as 7 here, there the value in column 17 would have been very much higher as in column 1. We have to compare column 1 and 17 here for this table and keep repeating our trials of our assumed value of a flux until column 1 and 17 they are near to each other. So I'll be explaining the same table again, and please listen very carefully. If any questions, please ask me after this. Column 1 is discharge. I guess it's clear right now. Discharge, given discharge, greater than given discharge, less than the given discharges. Given discharge is the maximum design discharge. It's not necessary that only maximum discharge is occurring. Most of the time, discharge less than design discharge is occurring. Sometimes there are chances design discharge greater than design discharge may occur. The downstream water level is given in form of a rating curve for all these normal, retrogression, accreted states. You have to assume a value of a flux as you did in previous steps. You have done all those steps which we did in setting crest level of the main weir undersluice. All those steps are repeated here in tabular form, and again a value of discharge is calculated. And now this discharge has to be compared with the first design discharge. If they are not near, revise the value of a flux. If they are Near to that means our assumed value of a flux will become okay. The purpose of this is to determine these water levels. And also we need water levels and plus the energy level. Water level plus velocity head, they are further used in our design calculations. For different states, normal retrogression are created, and for each state, different value of discharge we have determined water levels and energy levels. You see here in this table for 10 different scenarios calculations has been done. For actual design case, for your case, you can increase the number of scenarios. That is explained here that first column is concentration 20% reduction in design discharge by 50 and 75%. Consult for regarding column 2. This 2 is about column 2, consult the rating term for water level. Assume in column 3, assume a reasonable value of efflux. We have discussed flux is rise in water level in upstream of the Weir and Barrage. Column 4 is upstream water level, that is downstream water level plus efflux. Column 5 is depth, difference of water level and riverbed level. Column 6 is specific discharge given in column 1 over width of the weir. Velocity of flow Q over Y. In your case, that is ratio of column 6 and 5. Velocity head V is column square of column 7 was velocity. Velocity head is V square over 2G. Remember, G is 32.2 in FPS units. By mistake, sometimes uh, we use this value wrongly as 9.8. Remember this. Depth of flow passing over the weir is a flux minus the crest level, or head of water above the weir is a flux minus the crest level. Specific energy is column 8 plus 9. Let's see what for column 8 plus 9. Specific energy is velocity head, as capital H is denoting depth. Head of water, specific energy is 8 plus 9. Column 11 is Weir submergence. Downstream water level minus crest level. H over E naught to consult Gibson curve. Column 13, see a value of C dash over C from Gibson curve. Column 10, 15 is column 10 is about 3 over 2, E naught is about 3 over 2, specific discharge, total discharge. This column that is mentioned at the end, K, this column should be equal to column 1. If not, revise the assumed value of a flux in column 2. And a very important thing to remember here is every time a flux is changed, H over E naught also changes. H over E naught was calculated to see a value of C dash over C from a curve known as Gibson curve. So every time you change a value of a flux here, you also need to see a value of C dash over C corresponding to H over E naught. H over E naught will also change. Revise the value of C dash over C also. Then see what is the discharge. You may require 2 or 3 different trials to reach a nearer value. Same thing has to be done for the undersluice portion as well. First column, the input discharge, which is passing through the undersluice with 20% concentration discharge passing through undersluice is estimated at the end of step 4. The discharge we have calculated in previous slides, discharge which is passing through undersluices. I'll show you that was around 132,000 cusics. Rest of the table is similar to the previous except that here instead of width of the weir for calculation of discharge, we'll be using width of undersluices here. Charge passing through undersluices was calculated when we were setting crest level of undersluices. That is multiplied by 1.2 times the 20% concentration. 132 multiplied by 1.2. Downstream water levels, keep them as same as for normal retrogressive state. As I'm saying, 1.2 time concentration. For 1.2 time concentration means 600,000 cusics. So downstream water level 601.5, 595, and 604. 601.5, 595, and 604. Rest of the calculations are same. Assume a value of flux. Compare column 1 by column 17. If they are near, it's okay. If they are not near, try to be within plus 10%, 10 to 15%, or say stay within plus 15%, not greater than that. So do you see any mistake in this table? Any student? See please column 1 and column 17. If you see this table, column 1 and 17, I have done a mistake here that I have multiplied for retrogressive depleted state by width of the weir as 3000. 3000 is the total width of the weir. Remember, mostly the students will do that. They will prepare the first table. You copy this table, again paste it, and change the values. While changing the values, remember to change the width of the weir and to multiply this width of the weir used in column 17 as width of undersluices here. That is mentioned at the bottom also. Rest of the calculations are same. So total, this is you have to determine energy levels of the main weir and undersluices portion. In discussion, it might have taken some time. We have given almost 1.5 hours today and an hour earlier also. So we have discussed this for almost 2.5 hours. But if you see these calculations solved in the book, that won't take more than an hour. You have to give at least just around an hour to this chapter. You will be having a slightly changed value of design discharge, maximum discharge. The rest of the values will be same. Please keep this book in front of you and start with your value of discharge and solve up to this step. Step number 5. That is done on 1, 2, 3, 4, 5, 6, 7 pages on book. For these tables, you can use Excel also. Prepare these tables. These tables are very important for our further calculations. Both of these tables. Next steps, next 3 classes will be in next 3 classes we'll be picking values from these tables for further calculations.